And I'm still paying you. I got them hard ass beats like the crack of the tech. Still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats the bang of the average. Still paying you. I'ma make y'all pay for the dues.
All right, let's get started. All right, give it up for DBH Cash again. Awesome. All right, so quick reminder, I'm going to be gone next week. I'm going to London to see your boy, Fat Face Rick.
Oh, my man, Fat Face Rick.
Yes, so no class next week. In person, I'll record it while I'm remote, post it on YouTube, and I'll say hi to your friend, whatever. So, all right, and then Project Zero, that went out on Monday. That'll be due on September 7th. Homework 1 will be released later today, and that'll also be due on the same date. So again, Project Zero is the C++ project to prove that you know C++, and you can debug multi-threaded code. So please go, start that sooner rather than later, because you set up your dev environment and make sure everything's working. All right, so last class we were a bit rushed, but we talked about how the relational model was the superior data model for databases, and it pretty much is the fundamental way you would represent any major application database or data in a system. And then we also talked about how relational algebra is the building blocks for us to manipulate and query data in a relational model database, in a relational database system. And so today's class is really about we won't go back and look at relational algebra again. But now we'll talk about SQL, which is in a higher form of a query language than what relational algebra is. But then when we start actually talking about how to implement the system itself and actually execute the queries that we'll talk about today, that's when relational algebra will come back and sort of fit in. See, okay, now you see how these are the building blocks for building the system. Okay. All right. So let's go back to the 70s and the very beginning of SQL. So as I said, when Ted Codd wrote the original paper on the relational model in 1969, 1970, it was just the relational model and relational algebra. He didn't go into anything in details about the implementation of the system that could run a relational model, and he didn't say anything about what the query language should be. And so the other people at IBM picked up the paper and said, hey, this is actually a really good idea, even though IBM was making a ton of early money on a non-relational model system called IMS. And so they decided to start building a prototype in England. And the guys that invented SQL first developed a query language called Square. And it's considered it is considered to be the first relational query language, but nobody actually uses it because the syntax is pretty esoteric, and there actually wasn't a keyboard or any application to let you write code in it. Like you write things in this vertical manner. This is the classic example of getting the average salary of employees in a department, right? So again, so this was Square. Nobody actually did this. They threw it away. And then a bunch of the people that were working in England, they moved to San Jose in California at IBM Research, and they started building the first prototype, or the second prototype of IBM for building a relational database system called System R. It's very influential. A lot of seminal work came out of this. We'll see many times throughout the entire semester where I'll say, like, hey, this is a kind of cool idea, and here's a bunch of new systems in the modern era that actually implement it. Well, it turns out IBM invented a bunch of that crap in the 1970s, right? And so they first developed a query language called SQL, spelled out SEQUEL, in 1972, and this was Chamberlain and Boyce, and originally stood for Structured English Query Language. But then when IBM later then released a commercial product based on relational model and SQL in the 1980s, then they got sued because there was some other system or some other language out there was already using SQL, and they changed it to be SQL. Right? So sometimes you'll see people refer to like MySQL as MySQL, but a lot of the older guys back in the 70s, around the 80s, referred to it as SQL because that was the original name. So IBM released, they never released System R. They then later released other commercial systems like System 38. That's not really around anymore. SQL DS is around, but it's kind of in maintenance mode. But DB2 in 1983 was the big one that IBM put out, and that's still out today. I guarantee if you run any transaction online to some website, some bank, you're running on, chances are very likely some bank you'll be using DB2, right? There was other commercial systems in the 1970s. The first one was probably Oracle, which was founded by Larry Ellison. If you don't know him, he's the third richest person in the world. He owns a Hawaiian island, all paid for by databases. Again, this is why this class is important. All right, so SQL was originally, again, this proposal from IBM, but again, IBM was the juggernaut of computing back in the 1960s, 70s, and 80s. So whatever IBM did, that's what they said, everyone said, oh, yeah, that's the standard. The Oracle guys lucked out because they basically copied what IBM was doing. The Berkeley guys that built Ingress, they had their own querying language called Quell, but then when IBM put out DB2, SQL became the de facto standard. It became an ANSI standard in 1986 within the United States, and then an international standard in 1987. And then they've changed it to be the structured query language for SQL. So even though SQL is old, I just told you SQL was invented in 1972, 73, it's not a dead language, right? It's actively being used everywhere. I keep telling you how, throughout the entire semester, knowing SQL and writing SQL is super important. And they put out new versions of it all the time. The latest one came out in March 2023, where they added a bunch of new features like property graph queries and multi-dimensional arrays. So you ever heard of systems like Neo4j, dgraph, there's a bunch of other these graph databases. Now you can do all that in SQL. So the great thing about SQL is like it evolves over time, and as applications change and what people want to do with data changes, SQL gets added. They add new features to SQL to adapt to the times. And the challenge is going to be, and we'll see this throughout this lecture here, is that the SQL standard is going to say one thing, but nobody's actually going to implement it exactly. Every single data system is going to have their own quirks, their own little extra stuff they're going to sprinkle in. Sometimes they're ahead of the standard and they try to get whatever their version of a feature is into the standard. And sometimes the standard comes out and then they add it later on, but they still take their own liberties, if you will, with it. And we'll see what some of the biggest offenders are today in our demos. So if you have a data system today and you say you're going to support SQL, the bare minimum you need to have, say I have a SQL database, is what was defined in the SQL 92 standard. So this is your select, insert, update, deletes, your create tables, create indexes, the transactions. The very basic you need to say, SQL, that I have SQL, is that you follow the SQL 92 standard. But today's class, we'll go a little bit, talk about the newer stuff. And so people come along every 10 years and say SQL is a terrible language. It's not great. It certainly has its rough spots, but every attempt to try to replace it in the last 50, 60 years has failed. So right now we're in the phase where all the AI guys are saying, oh yeah, SQL is going to die. You can use LLMs for everything, yada, yada, yada. So this is the guy working on a system called Vespa. He's basically saying natural language can replace SQL. This guy is like a crypto bro and he's trying to sell some video demo or some video like Code Academy thing, right, where you can use ChatGPT to replace everything with SQL. So I'm not here to say that SQL is not going to be replaced in my lifetime. It may be, but it's very unlikely. Like, it was here before you're born. It'll be here after we die. So it's not going to go away. But when you sit down, are you going to immediately write SQL in many cases? Oftentimes, no. Right? Yes.
So what is the things that might replace SQL?
The question is, what would replace SQL? I don't know. So we did a seminar series last semester. We had all the people that are trying to replace SQL, talking about how they're going to replace SQL. The closest one that I think could not replace SQL but extend it is actually Google's pipe SQL syntax. And I can give a little demo of that in a second. What's that? You were at Google? Yeah, so that thing's...
Yeah,
oh, you wrote it. Okay, yes, so there you go. So that's probably the closest thing, but it's still fundamentally, it's an enhancement to SQL. Right. What's that? The question, what keeps it going? Again, going back to this, it evolves, right? Like, here's all the different versions. Like, say 15 years ago, what was the hot database? MongoDB, because of Web 2.0, whatever the buzzword was at the time. You were storing everything as JSON. Well, the SQL standard now adds support for JSON. 30 years ago, 20 years ago, XML was the hot thing. Well, SQL supports XML. The statement is the flexibility of the SQL. SQL will provide you a basic building block that you can then add more advanced features and do additional things, right? Now, again, I mentioned, like, are they doing things? Is it perfect? No. One of the biggest complaints is that the select clause comes before the from clause, right? Well, in the original proposal from IBM in the 1970s, the from clause came first, then the select. But then they did a user study at the Arizona State University, and all the students, whatever they tested, said, "Oh, we like the select before the from." And that's the way it's been for 50, 60 years because of those people, right? Well, we'll see some data system we can play around with and see how you can change things. And sometimes you don't always have to have it in that order, but in general you do. All right, so again, I've said many public statements before that SQL is the most important programming language you need to learn as a student because again, no matter whether you're actually building a database system or just using one, the rest of your life you're going to come across SQL. And maybe the LLMs can provide you a first draft of a query language. Maybe it'll end up being like assembly where there's the high level things we can write and then that gets transpiled down to SQL, which is what a lot of replacements to SQL are trying to do. But everybody has to learn SQL. It's very, very important. And so to give you an example of how serious I am about learning SQL, let's see the audio up here. Oh, there's no audio. That sucks. Well, this is my 5-year-old biological daughter, and every morning we wake up at 7 a.m. and she has to write SQL before she can have breakfast. Is that considered child abuse? Anyway, I tell her mom loves her more when she writes SQL, and it works. Okay. All right. So what is the relational language give you? What is SQL going to give us? There'll be sort of 3 basic components: the DML, DDL, and DCL. DML is the data manipulation language. When you write a select statement or update, insert, update, deletes, those are all going to be DMLs. The DDL will be the definition of like a table, an index, or a view. And the DCL will be like ACLs, like controlling who's allowed to see what data or what columns and so forth. There's other things we'll cover later in the semester, like transactions, like how to call begin transaction and roll back and things like that. But we'll worry about that later. One important thing we got to understand also too is that although the relational model is based on sets, right? We looked at unions and intersections. That was basic set theory. SQL is going to be based on bags. So sets are unordered collections of data where you don't have duplicates. Bags are unordered collections of data where you do have duplicates, right? Lists would be a ordered collection that has a defined order. Bags and sets do not. So that means that in SQL, they're going to make this choice to allow duplicates because it requires extra work to remove the duplicates. And so if you really want to remove them, you have to add extra keywords like distinct and other things to remove the things that you don't want. So by default, we'll have duplicates. And most of the times it's not a problem, but if you do care about removing duplicates, there's SQL allow you to do this. All right, so we're going to be a quick crash course on the basics of SQL, but I want to cover the things that are on the more modern in the in the spec, and we'll look at some examples of how real systems actually run these things. And then for today, we actually have one of our first flash talks for the semester. So the guys from DBT are going to come give a talk about their system. Who here has ever heard of DBT or used DBT before? One. Okay. It is one of the most widely used database tools in the world today. It's basically, if you're a data scientist or doing any major data analysis, chances are they're running on DBT, right? It's pretty significant. And guess what? It's just based on SQL. It's SQL with templates, right? So they'll show you, he'll talk about what they're doing over there. And then they'll come, come give a pitch for recruiting later in the semester. Like one of our best students from 445 last year, she's there right now. All right, so today's class, the example database we're going to use will be just a really simple representation of a university, right? There's a student table, there's a course table, and then students take those courses and they get grades, right? So we'll just use this as the running example throughout today's class. All right, so the very first thing we want to do is aggregations, right? I'm assuming everyone here has seen SQL before, so you know how to do basic selects, inserts, update, deletes, right? We don't need to cover those things. But now we want to start extrapolating new data or new information from the data we've already collected and put it into our database. So aggregations are the basic formula of how to do this. The idea is that you're going to take multiple tuples or multiple values across multiple tuples, and we can coalesce them into a single scalar value that computes some aggregate function, like an average, min, max, the count. So other systems can support things like standard deviations or geometric means. The basic idea is you're collapsing down multiple values and producing a single output, right? So the aggregation function can pretty much be used only in the output list or projection list of our SQL query. Not always the case because of nested queries, but for now we can ignore that. And so you can do really basic things like you can say, count the number of students that have an @CS login, right? And then in our projection output list here, we see we have a count function that's computing just again for every student that matches that predicate. I think of the filter from last class. My projection output is going to maintain a running tally of the number of students that it counts. But notice I have count with the login field in there. Does that make any sense? Does that sound right? Well, what does it mean to be counting logins? Well, it turns out for some functions like count, that doesn't actually matter what you put in there. I can do count star, produces the same answer. I can do count 1, produces the same answer. You can put count 1 plus 1, like whatever. Okay, because at the end of the day, all it's really doing is just counting the number of tuples that get matched here, right? So that's a basic aggregation. If we try to do things like have multiple attributes in our projection list, in addition to an aggregation, we can have some problems, right? So in this query here, we're trying to get the average GPA of the students enrolled in each course, and obviously now we want to include the course ID, right? Because we want to know what course the average is being computed for, right? But is this correct? Shaking his head, no. Why? Well, he says it's group by. That'll be the answer, how to fix it. But like, what does it mean to compute the average GPA of all the tuples, but then spit out some kind of course ID, right? What's that? The statement is there isn't a canonical one that should be part of the output. Correct, right? So this is invalid. Most database systems will throw an error and say you can't do this. SQLite will let you do this. MySQL used to let you do it, doesn't let you do it anymore. And so the way to get around this would be you just put, you can put any value in there. Right? This is something new that SQL added, and it produces some output. Is this correct? I don't know. But like from the database system's perspective, you told it what you wanted, and it computed it for you. Right? So he brought up the way to solve this is to do group bys. So group by is a way to partition or cluster the data as we're scanning along, so that when we compute our aggregation, the aggregation will be derived from each group, each cluster. So again, the query is I want to get the average GPA for each course. So I add my group by clause with the course ID, and then say this is my original table. Now when I scan through, I can look at the course ID and basically keep track of where the boundaries of these are. And then when I compute my aggregation, I know to compute the average per group. I didn't say how to implement this, right? The data system is doing this for us. You could either build a hash table, you could actually sort things first, then do the group by. We'll cover how to do that later in the semester. But at this point in the class, just trying to say like, hey, look, I can group things up, and the data system will figure out how to make sure I produce the right calculation. Right? You can go even more sophisticated with group bys with what are called grouping sets. There's also a thing called roll-ups and cubes. We don't have to worry about that. But say you want to do something like I want to compute multiple aggregations on my data, but I want to be able to do this in a single query. Now I can do the union operator that we saw last class. I can add that to SQL and do a bunch of separate queries and mash things all together. But if I can tell the data system that like this is exactly what I want and kind of put everything together in a single package or a single query, then although we said it's just be declarative and we don't have to tell the data system how to actually execute the query, we can be nice to it and actually produce queries for it that it has a better time reasoning about and crunching on. So you have group by, and then you specify that you have a grouping set. And then now within my grouping set clause, I can specify the separate group bys that I want. And each of these will be executed as if they were a separate query. But really what's happening is it's scanning through the data once and computing this answer for you and sort of mashing everything together all at the end, right? So the first group by say group everything by the course and the grade, then group everything by just the course name, and then give me the overall number for the total. So this is trying to count the number of students in each course, by each course and by each grade, by each course, and by total across all students. What about what, sorry? Okay, yeah, okay. All right. So again, just think of like, and these are like groups or clusters. So here's the red one, right? There's the blue one here at the bottom, and then the overall total is at the top. And then for the cases where the output doesn't have the column that's being grouped on, they'll put a null there. It's kind of funky, but again, the one reoccurring theme we'll see with queries is that we want to reduce the amount of back and forth between we have the database server and the application, so we can give as much information all in one single query, give it to the database system. It can ideally do a better job at running this more efficiently than it would from multiple round trips. Is this clear? All right, let's say I want to do some additional filtering after I've done my aggregation with the group by. Well, SQL supports that with the having clause, right? And the basic idea is that I want to be able to filter things out based on whatever is being computed as part of the aggregation, right? So in this case here, on my where clause, I want to filter out all the students, or filter out all the courses where the average GPA is greater than or less than 3.9. So I want to get the ones that are 3.9. But what am I trying to do here? I'm trying to reference average GPA, but that's being produced as the output in my projection list for my select statement. So at this point, again, think of like the data system is actually executing this. You're scanning through the data. You're trying to apply some filter. You don't have this average computed yet, so how do you know whether to throw away a record or not? So you can't do this. And instead, you want to do this through a having clause, where now I can put what my filter should be at the bottom. Now, in some database systems, they're really strict about what's down here in the having clause. Right? Again, I have an alias for the average GPA. I'm calling average underscore GPA, AVG underscore GPA. In some systems, you can't do that either, because it doesn't know about what the alias up above is at its point as it's scanning. And I sort of said SQL is not supposed to be about thinking about how things are actually going to be executed in like what order of the operations. But in some cases, it actually is that case, or in some cases, it is that way. So some systems won't let you do this, and instead you have to repeat the actual average, the aggregation you want at the bottom here. I mean, Postgres requires this. Yes.
So the from where clause is effectively just a join.
The statement is the from where clause is effectively a join. Oh, sorry. Yeah, sorry. Yeah. So right here I have from enrolled as E, comma student as S. Yes. So. No, let's not talk about teaching product. So in this syntax here, because I didn't explicitly say join, this is like the old way of writing it without explicit join. Don't do what I did here. You should always include join. But the databases will be smart enough to recognize that I have my EID, E.SID equals S.SID. So it would know, okay, well, this is from this table here. This is from that table there. I got to join. And it's an inner join. It'll do that before the Cartesian product, ideally. Yes.
So if you are using the average function in the having clause, is this system wrong having the application like 2 times or really wrong at the time?
All right. So this question is: I have the average aggregation in both the having and the select output. Is the data system going to be stupid enough to run both of them? Hopefully, no. But there's no guarantee. But ideally, yes. Like most systems will be smart enough to know not to do that. Just for whatever reason, some systems don't let you reference the alias things up above. Other questions? Okay, right, and it produces the output like this. All right, so that's the basic for aggregations. And again, with some slight nuances about what the having clause looks like and what the grouping sets may look like. In general, most database systems will support all the things I just showed you here today, right? Next, we'll talk about different things you can do to start in different data types. We'll start with strings. That should be mostly the same across different data systems. Then we'll come to dates and times, and that's when it all falls apart, right? And although the first homework for you guys will be based on DuckDB, that's really because it's a great system and it runs on every single laptop or every single machine you have. It still runs on the Android machines, even though they're running an old version of Ubuntu here, right? There isn't another, other than SQLite, there isn't another system we could give you that could run everywhere. But I'm not trying to say like, okay, you're learning DuckDB SQL syntax. It's really, I care about, do you understand what you can possibly do with SQL at a high level? Because when you go out in the real world or use different database systems, again, all these nuances that we'll talk about here, they're going to be, every system will have their own little quirks and be slightly different. So if you understand the fundamentals of SQL, then you can take that and go understand how to apply that knowledge to different data systems. I would say it is easier to take a SQL dialect from one system and apply it to another. Now, it's not going to be a one-to-one. It's not going to be. I'm not trying to say you can take SQL and just like do search and replace and it magically runs on the next system. There's a lot of people who spend a lot of money trying to convert from one system to another. I'm just trying to say that like it would not take you a lot of time to get up to speed pretty quickly with a new system. Like going from Python to Rust, that's a major lift. Going from MySQL to Postgres, again, mentally less so. Okay? All right, so there's string data types, of course. The SQL standard says that any string you store in a database will be case sensitive, and you can represent them or the constants of them as single quoted strings. Most systems follow that. MySQL is going to be the dark horse here, where they're going to be case insensitive for whatever reason, and they're going to support both single and double. So let's see what happens when you do this. Can we all read that, or should I make the screen? Is that better? Oh, it's too dark. All right. Wow. What? All right. Let me log in with my laptop here, because it's a pain to type on the surface here. All right. So I said that strings were uppercase. Sorry, in the SQL standard, strings are case sensitive, and you represent them with single quotes. So this is Postgres. So I can do select star. I couldn't until I lost connection. Awesome. There we go. So we'll look up the student table. Where name equals Riza. Right? Nothing shows up. Make sure I have capital. See, so that doesn't work because it has to be a capital A, right? Why is this going so slow? Sorry. You know what it is? I think I'm uploading your videos from last time. Let me get rid of that. Sorry. Much better. All right. So if we now try this in MySQL, right? That works, but I can also do this, right? That seems kind of weird, right? I can also use double quotes. And that works. If I go try the exact same query on other systems, it should not work. So this is Postgres. Sorry. Doesn't work because I do that. Right? In Postgres, the double quotes is meant to represent an escape like name of a column or table. Like if I have a table with a space in it, I can use double quotes to take care of that. Over on my SQLite now, doesn't like it is case sensitive, but it lets me do the double quotes. In DuckDB, it's case sensitive. Here it's complaining it's because it's looking for the name of the column. So I have to escape it with single quotes, and then it is case sensitive. We'll come back to ClickHouse and Firebolt and SQL Server in a second. But again, just trying to show you that like a basic thing like, hey, strings, they're going to be different. So there's basic string operations. There's like if you want to do wildcard matches on the string, SQL standard specifies the like clause, and then it doesn't follow maybe the general, more common regular expression syntax you might see before with like stars and dots and so forth. The % sign is meant to represent any substring, including empty strings. And then if you want to put match a single character, you do an underscore. So this is trying to get all of the students that are enrolled in 15 followed by a wild card, all the 15 courses, and you would use the like clause for that. If this is case sensitive, you want to be case insensitive, you would use I like. Yes. His statement is, are the field names and table names always case sensitive in SQL? Depends on implementation. Postgres will automatically lowercase any table name you give it. Other systems don't do that. I have no idea what the SQL standard says. All right. What's that? The statement is, if you use in Postgres, if you use double quotes to name a column, does that will that give you escaped? I don't know. Let's find out. Create table. Sorry. Create table. You want to use XXX like that with an int field. Yeah. All right. So Postgres took it and maintained it. So, but if I do this, can I do select star from Wi-Fi? Sorry. Select star from XXX. Yeah, I didn't know about that. Yeah, so his point, by default, unless you quote it in Postgres, you will not get you will not get the case sensitivity. All right. Right. So again, if you want regular expressions, the SQL standard specifies this clause called or operator called similar to. Postgres supports this. DuckDB supports this. Many other systems do not. Instead, they have their own regular expression syntax. Again, a good example where SQL standard says one thing, systems implement other things. There's a bunch of built-in string functions that you can do just to manipulate strings as one would expect, like substring, lowercase, uppercase, and so forth, right? And most systems have the same implementation of these functions, roughly provide the same semantics. To something really basic like a concatenating string, this is where things go wrong as well, right? The SQL standard specifies that you have a double bar to say I want to concatenate two things. In SQL Server, it's the plus operator. And then in MySQL, I should test this more recently in the newer versions, but they don't have either one. You have to run an explicit concat function, right? Again, this is painful. It's annoying, but it's not the end of the world, right? You can easily navigate this from going from one system to the next. But let's talk about dates and times, right? Obviously, in our database, yes, question.
So when you say most systems don't support it, when you're talking about SQL 92, that's the ISO standard in SQL language, right?
Yes. So this question is, when I say most systems do support it or don't support it, do not.
Do not support it. That means they are not using ISO standards?
So the SQL 92 would give you like the basic select, insert, update, deletes. The things we're talking about today, and like they're actually so far everything we're talking about today is back in the SQL 92 standard, and so they're off slightly on this one thing. There's no system in the world that I'm aware of that implements exactly the SQL 92 standard as written. They're always going to be slightly off. MySQL used to be the worst offender. They've gotten better in the last 10 years.
So when you showed the SQL 2023, what are these MySQL, SQLite supporting that standard, or does that need to be a new database system altogether to support SQL 23?
His statement is, when I say the SQL 23 standard came out, who actually supports that? Again, nobody. So property graph queries, the only system I know that supports that is Oracle, because Oracle was pushing to get that in there. I'm pretty sure Postgres doesn't support it, DuckDB doesn't support it, right? The other commercial vendors, same thing. That's not to say they won't, it's just they haven't got to it yet. But it's like, will they implement it exactly as written? Probably not, because for whatever reason, right? Again, MySQL had all sorts of weird stuff. And then we had the guy that invented MySQL gave a talk with us, it was last semester. And I asked him at the beginning of the talk, it's not recorded, like, hey, what's up? Why did you do all this, right? And he's like, oh, because we just did it. What's the 90s? I don't know. This is what he said. Right? It's oftentimes, it's many times, it's like some guy sitting there. It's like, oh, I'll do it this way. And then everyone's like, all right, good. Right? We'll see this when we talk about lateral joins. Lateral joins was in the standard. My understanding is the Microsoft guys didn't know it existed, and they made their own called cross-apply. It has basically the same semantics as lateral joins, but they don't call it lateral joins, they call it cross-apply. Right? Again, there's so many implementations out there, nobody actually follows it. All right, dates, times, this is where it gets rough. So the SQL standard specifies a basic date and time type. I think it also has times with time zones. Right? By default, you get whatever the time zone is on the data system where it's running when you insert a record. If you're lucky, maybe UTC is a time zone always. Not always the case. If you explicitly want to know what the time zone is, you want to store that in the type with it. But again, not every system will support that. This is my favorite demo to give every year. We're going to do something which seems like it should be really simple to do. We're going to compute the number of days from today, August 27th, 2025, to the beginning of the year, January 1st, 2025. Right? It seems pretty simple, but as we'll see, every system is going to do something slightly different. How to get that answer. All right, so in all right, so we need to get dates. All right, so how do we get the current date? Well, in the SQL standard, there's a now function, and that'll give you out the current year as a timestamp, right? Or the full timestamp. So we go along now to our different system. This is MySQL. MySQL has it. That's great. Go to SQLite. SQLite doesn't have it. Okay. Let's go to DuckDB. DuckDB follows the grammar from Postgres. Like they literally have like a copy of the Postgres grammar, and they're using that. So a lot of times what Postgres has, DuckDB will have. Let's go over to ClickHouse. ClickHouse has it. That's good. Let's go to Firebolt. Firebolt's got that. So that's good. And then last one is SQL Server. For reasons of the 1980s, I don't fully understand, you have to write Go after every query. Because it wants to do like a batch, right? And this is for this one client. Other clients, there's other clients that they don't have to do this. For the one that Microsoft gives you, you always have to write Go. All right, so they complain they don't have now. All right, well, there's another way to do this. In this SQL standard, I think you can also get a, you can get something called current timestamp, right? So this is Postgres, except Postgres doesn't have it. They don't have the function, but they have the keyword. Let's go to MySQL. Sorry. They have the function. They have the keyword. Let's go to SQLite. SQLite doesn't have the function, but it has the keyword. DuckDB is going to have doesn't have the function, but it has the keyword, just like Postgres. ClickHouse has the function, does not have the keyword. Firebolt has the function, has the function, does not have the keyword. And then SQL Server, I gotta write Go, does not have the function, but it has the keyword. All right, well, that kind of sucks because, like, again, nobody has the same thing. So this turned out to be really easy to do in Postgres in a bunch of systems. So what I can do is take the date as a string, so 2025 on the 27th, and then cast the beginning of the year, cast these as dates, and just subtract them. And make it 238, which is actually correct. So what am I doing here? This cast function is taking the string, and I'm telling it I want to cast this data, this constant string I'm giving you, cast it as a date. For whatever reason, you got to put as. Oh shit, you can't even see that. Sorry. Please say something next time, because make sure this looks good. All right, there we go. And probably it's going to be. Let me shrink it over here. Okay, there you go. All right, so Again, I take the string, I call this cast function, and I say I want as a date, right? So that's fine. What I like about in one example of an idiom in Postgres that I like a lot is that instead of calling that cast function, I can put 2 colons at the end of any piece of data, and that tells the data type I want to cast into it, right? So that's nice. So I can cast my strings to a date. So that works great. So let's pop over now to try to do the same thing in MySQL. I get this, 726. Again, just as a refresh your brain, there's not 726 days in a year. It's 238 days since the beginning. So what is this number? I didn't know either. Some rando in YouTube, in the YouTube comment of all places, posted what it was, and I'm like, oh, he was right. So what this is the first number 7 is the current month of August, 8, subtracting the January, 1, you get 7. Then you get the same thing for the number of days. So what's happening here is that MySQL is casting the date as an unsigned integer like this. We're just mashing together the year, the month, the day. And so it's really computing this. All right. That sucks. There's your 726. So turns out there's actually a date diff function in MySQL where I can easily get back 238 days. Okay, well, let's go back to SQL Server, or sorry, to Postgres. And of course, they don't have it either. All right. All right, so let's see how to do this in SQL Server. We'll come back to the other ones. SQL Server, you can cast things as a date, gotta write go, right? And I get a date like that. And then they actually have the date diff function. Here I go, and I get 238. But notice now I have this new thing here. I have this get date, right? Where that's different. Didn't see that before. So let's see whether anybody has that. MySQL doesn't have it. Postgres doesn't have it, right? So you see where I'm getting at. All right. So let's try this now in ClickHouse. Actually, to prove that this works in, let me prove it works in DuckDB and in Firebolt. So let's go to DuckDB. I can do it the Postgres way. Boom, I get the right answer. I can do this in Firebolt. I do it the Postgres way. I get the right answer. All right, so Firebolt, DuckDB, and Postgres are doing the same thing. So that's good. If we go back to our boy ClickHouse, so we tried this before. That produced the right answer. That worked out pretty well. ChatGPT gave me this, right? But it's complaining that it doesn't know about this today function. Okay, well, I've never seen that before. I said it was now. What is today? They don't have it. Does MySQL have it? Nope. All right, well, the documentation of ClickHouse says they have it, but it's actually case sensitive. It's lowercase today. Then you get that, right? Right, exactly. So before, I think we did now, right? That's uppercase. Okay, can I go now? Yeah. So now can do uppercase, lowercase, but today cannot. Awesome. All right, last one, SQLite. So they don't have date diff. So if I try to do it the Postgres way, I get 0. Well, that's not good. So I actually came up with the same answer that ChatGPT came up with, where you convert the timestamps into the Julian calendar, which is the number of days since 452 BC or whatever. Like Julius Caesar converted everyone to the Julian calendar in like 45 BC. But the dating goes back even farther, right? So you can do something like this, and you get 238, but it's a decimal. So if you cast it as a you cast it as an integer, you get 238. Another way to do this would be to convert this to the Unix epoch. If you know what that is, right? It's the number of seconds since the dawn of Unix was like January 1st, 1970. So you can convert it to that, convert the current timestamp to that number of seconds, that to the beginning of the year to the timestamps, divided by 60 days or 60 seconds by 60 minutes times 24 hours. And why is it integer? Because it's doing some kind of casting. Yeah. Which is, I don't want to get into type conversion because this is CMU and people get really uptight about it. But yeah, that's another problem here. All right, so the main takeaway from all this is just like a really simple thing, like let's calculate dates, and things go wrong. All right, so let me skip through output control or get through this real quickly. You can do order bys. If you can, again, SQL or relational models unordered. If you care about order, you can add order by clause. Since the relational model is, or SQL is also, it's unordered, and if you care about the order, you would add order by, but sometimes you maybe don't want all the results. You can add a limit clause or a fetch offset clause, where you basically say, I only want the first 5 rows or first 10 rows, and you can even offset it. And then you can specify what to deal with when you have ties, or if two tuples should be part of the same output, what do you do? The shorthand way is to use a limit clause. That's not in the SQL standard, but many systems support that. At least the DuckDB and Postgres do, MySQL. And then SQL Server has their own syntax of saying top 10 in the front. Right, so jump along here. So as I said, many times what you want to be able to do is have a single SQL query produce all the answer without having to go back and forth the application. So you can take the output of a SQL query and put it into an actual a table or a temp table, and then do additional queries on that. So in the SQL standard, you say select with the into clause, and then where it says course IDs, that's the name of the table I'm going to insert into. In Postgres, you can actually specify that it's a temporary table, so that when you close the client, the table gets blown away. But that's not in standard in all systems. All right, so let's jump into the more challenging things in the last half an hour. So nested queries, CTEs, and window functions. So many times you're going to find yourself not being able to express what you want to compute within a single select statement. And you actually maybe need to use multiple select statements. And as I said, you could write your inmate result out to a temp table, but oftentimes you may be able to just do a select inside of an existing select. And so these are called inner queries or nested queries, and they can appear pretty much anywhere in a SQL statement. So I can do something really simple like this, where I have a select statement, what we'll call the outer query, the top part here. And then inside my where clause, now I have another select statement called the inner query, where I'm computing some answer that can then be used or leveraged in the outer query. All right. So this is an example of putting in the where clause. You can put it in the projection output. You can put it in the from clause. I think some systems let you put it in like the group by clause, the having clause, which is not a good idea, but you could do that. And so we're not going to talk about how to actually implement this or execute this efficiently just yet. But it's obviously the dumbest thing to do would be treat this as like 2 nested for loops, where say in the top one here, for every single student, I'm going to then run that inner query in its entirety for to try to find a match. MySQL used to do that. Most systems, when they first start doing nested queries, they do that. And obviously that's very inefficient because the answer is not going to change from one tuple on the outer query to the next. So we'll talk about this later after the midterm, but ideally what you want to be able to do is rewrite that query into a join, because the data systems know how to execute joins very efficiently. And so you can take if you have a nested query like that, if you can convert it to a join, it'll run much faster. But not every system can do that. Postgres is actually very bad at it. The statement is there might be some cases where the subquery is actually faster. So this is getting the weeds, but like you can imagine something like a computing aggregation, like a max ID. If I could run that once, cache the result, and use that, then yeah, that would be fast. But I mean, you almost never want to run. I don't think you ever want to run the inner query over and over again. It's like stupid. The question is, what system was actually good at converting these things? there's a system called out of Germany called Umbra. It's been written by one of the best database system researchers in the world. And he has a new paper that came out this year where he can handle basically any nested query he can rewrite. Statement is, well, making it more mainstream systems. So DuckDB does an earlier version of what he did because they just copied what he did because it was in the papers, right? But one of my PhD students here came up with a nested query that actually would break DuckDB and broke this other system. It won't work correctly. It runs out of memory because it blows up. Because it's just thinking like you're just generating a bunch of intermediate results, and the intermediate balloons up and you run out of memory. So the newer version of this German system called Umbra, which is now commercialized as CedarDB, that system actually supports it. This all I have to cut on the video. I can't see this. Yeah, so we buried the bodies and the cops never said anything. That's the way it is. All right. So nested query. So let's see. We want to get the names of the students that are in 445. Right? And so when you start doing homework 1, you got to think about how you're going to construct these things. With nested queries, you want to sort of maybe start with the outer query first and figure out what you want the final output to be. And then oftentimes I'll just write maybe in like natural language what the inner query should be. And I figure out how to sort of, how to rewrite that inner query to fit into what I want in the outer query. So if I want to get all the names of the students that are in 445, I know I want to do select name from student with some kind of where clause. And my where clause is going to say something like, get the list of the people, the set of people that are taking 445. So my inner query would look something like this, but now I need to mash the two together. And so this is where I can add things like an in clause or other operators in my expressions to specify how I want to link together the inner query with the outer query. So in this case here, I'm saying where SID is in, and then some nested query here. So this is just doing set membership. I'll match on my outer table's query, or the outer query, any record that has an SID that is in my set that is produced by the inner query. And to his point, he was saying before, sometimes it's more efficient to run the nested query without doing a join. And obviously, in this one, it's pretty obvious that you want to run that query once, the inner query, and be able to reuse the result over and over again. And a join would basically do that for you. So notice also here too that I'm now referencing the student ID in the inner query. That's going to get bound to the enroll table inside the inner query, and then the student ID is getting bound to the one on the outside. There are things like correlated subqueries where you can match things on the inside with the outside, but we don't have to worry about that just yet. All right, so you can do a bunch of different operators to specify what the matching should be. My example I did before was in, which is equivalent to equals any, but you can say all have to match, at least one has to match, or none has to match, right? You can do a bunch of these kind of operations. All right, let's more complicated things. Let's find the student record that has the highest ID that is enrolled in at least one course. All right, so the outer query, I know I'm going to want to say I want the student ID and their name, and then the inner query is going to be something like, is the highest enrolled student ID? So my inner query could be like this, right? I want to get the max student ID from enrolled, and I want to match that with the student on the outer query, right? And I just, instead of writing in equals any or equals all, I'll just put in the in clause like this. This is one way to do this, right? You could do this with sorting the table and then fetching the first row. That would be the max. I can put the max query, the aggregation, inside the join clause, right? There's a bunch of different ways that you could write queries to produce the correct answer. I'm not saying one way is better than another. It's going to depend highly on what the system can actually support and run. In theory, SQL, again, it shouldn't matter, but oftentimes it does. For homework 1, you're running on DuckDB on your local machine. There won't be a huge difference in performance writing different things. At least there shouldn't be. All right, look, so one more example. Find all the courses that have at least that have no students enrolled in it. My outer query should be select all the courses, and where I want to match where there isn't a tuple for that course in the enrolled table. So I can do something really simple like this. I can say select star from enrolled where course ID or the course ID, and when the old table matches the course ID from the course table on the outside here. And then notice how this inner one here is being bound to the one on the outside, right? So this is called a correlated subquery where the the result being computed on the inside depends on whatever tuple you're looking at on the outside. And many systems can't do that, can't convert that into joins. But now SQL Server, DuckDB, and this German system, CDB and Umbra can. All right, so when you do homework 1, sometimes it'll be obvious that you want to use a CTE, which we'll cover in a second. Sometimes you want to do a nested query, but in general, it's up to preference. Okay, we'll see CTEs in a second. Lateral joins are a special kind of join where it allows a query that's technically at the same level of nesting within one query to reference data in another query at the same level. So what do I mean by that? So think of it like it's 2 for loops where I can now have a previously executed query within my same sort of outer query be referenced by queries that came after it. So I said before that in SQL, that ideally in a declarative language, you don't want to specify what the order of the operations should be, but in something like a lateral join, you do have to specify because you have to know like this thing has to get computed before this other one gets computed. So there's a really toy example, select star from a derived table where I have select 1 as X. So this is making a synthetic virtual table that has one tuple with one value of 1. And then now I have my lateral operator. And in the second query here, I'm now allowed to reference up the nested query that came before it. And it's roughly equivalent to producing the output of this Python code like this. I'm seeing a lot of confused faces, so let's look at another example. So I want to calculate the number of students that are enrolled in each course and get their average GPA, and I want to sort them based on the enrollment count in descending order. So the outer query, again, is going to be select star from course, when all the tuples that are all the attributes for anybody that's in a course or any course tuple. The first lateral query is going to be for each course, compute the number of enrolled students, and then the second lateral query will be for each course now, compute the average GPA of the enrolled students. So it would look roughly like this. So in some cases, in some versions of SQL, you have to specify that it's a lateral join explicitly with like a join operator. In this case here in Postgres, you can just say I have a lateral, and then you have a nested query, and then that can do whatever wants inside that. So the first one here, again, we're computing or counting the number of students that are enrolled in each given course, right? So in this case here, the course ID I'm referencing is going to come from the outer query. The second one down here, where I'm computing the average GPA for every student that are enrolled in the course. Again, same thing here now. This course ID can come from this outer one here, or it could come from the one in the middle. It doesn't matter. They're actually both semantically correct. They would both produce the same result. Right? And you would get something like this, and I would sort again by the count in ascending order. All right, let me give show you quickly what this looks like. So DuckDB, MySQL, Postgres, and Fireball are all going to produce the same result for lateral joins, which is nice. Sorry, say it again? For that, he's saying, could you do that with a normal join? For that example, yes. Actually, in the sake of time, let me get through CTEs, and because we have the caller, the speaker today, and I can always show what this looks like afterwards. All right, CTEs are common table expressions. This is a newer construct in SQL. Think of this as like, instead of having two separate select statements, one to create a temp table and then another to query that temp table, I can create a temp table within my query that then gets populated and materialized, and then it gets thrown away when the query is over, right? So the way this is specified, I have my with clause at the top. I give a name of my CTE, or sort of the name of the table. Whatever the columns are going to be is the output. Notice I don't have to put the types, because it's going to derive the types based on whatever's inside of the as clause here. And then now down below, after the closing parentheses, I can then reference that CTE as if it was like a real table. You almost think it's like a macro, where I'm like I could take whatever's in that with clause and inject that as a nested query here. Statement question is, can you parameterize it? What do you mean by that?
Like, can I say that I pass it
Oh,
a different value for like specific part?
yeah. So the statement is, can you pass in a value that causes the
With the different values type.
I don't think you can. We can take this offline. There is research where you can take a arbitrary procedural code like Python or whatever, Pascal. Or people write these stored procedural functions in like this language called PL SQL. There's ways to automatically convert procedural code into CTEs, which they do. It does look like this, but now you're actually maintaining a state table, what the input is, to basically mimic the same thing. That is not. You don't need to know that for this. Okay. All right, so quick example. Now I'm going to find the student record with the highest ID enrolled in at least one course. We saw this before. Instead of doing a nested query, I now have my CTE, where I can do a join against it. And so the data system could be smart enough to know, compute the CTE once, and then fill in the value and use that later on. It's nicer syntax than using nested queries, because you sort of declare them up front and then you can reference them down below. Whereas nested queries, you kind of have they're embedded and makes the SQL quite large.
But nested queries can reference like inline.
The statement is, yes, nested queries cannot reference inline things, correct, yes. But sometimes this is okay. All right, the last thing I want to cover is window functions. So in all the aggregations and things we talked about before, you can't easily keep track of how things are being processed, the order that you're looking at them. So you can't compute things that require a notion of ordering, because again, SQL is unordered. But sometimes you want to do things like a moving average. I think of like a time series data set where I'm having different timestamps, different times throughout the day. I'm recording the temperature. So I want to say, what was the moving average of the temperature at this given time? Or stock price would be another good example of this. But with window functions, you can now do this and now generate multiple aggregation outputs as you logically scan along the data in your SQL query. So it's sort of like an aggregation, but you're not grouping them to produce a single output. You could have multiple outputs for every single tuple. So the way this works, you specify in your projection list, you have a function name, and it'll have basic aggregation functions and additional functions that are specific for window functions. And then you have this over clause to specify how you want to split things up or slice things up as you go along. So the aggregations can be anything we talked about before. Like again, if I want to compute a moving average, the min, max, the count of some window as I scan. And then the special functions are row number and rank. So row number would be like what offset you are in a group as you slice it up, and the rank would be the position according to some sort order, right? So my query is select star from the enroll table, and I'm going to compute the row number without doing any slicing or any group bys. And so now you would see that I'm introducing this new column here called row number that keeps track of where that tuple's position is within that group of the window. If I want to, again, do something like a group by, they have a partition by keyword. So now I'm going to compute get the course ID and the student ID for everyone enrolled in a course, and I want to know what the row number is as I partition them by the course ID, right? And so again, just like the group by clause, row things up in the groups when I produce my output, same thing here. Now you can see the row number gets reset back to 1 every time I enter a new partition or enter a new group. I can sort things within my group as well, right? So in the over clause, I can specify an order by, and then the second time I'll have to go this, pass over this, but you can do more complicated things in there. All right, so to finish up, again, SQL is very important. It's not going away. There's this survey the IEEE does every year about what students say are the most important languages they need to learn. SQL is always now number 1. Python's number 2. Number 3 is Java. All right. So again, as I said, for the rest of your life, you're going to come across SQL, and it's really important to at least know the basics of it. So homework 1 and this class right here today will provide you the foundation you can then expand upon in your further careers. All right, so homework 1 is going out today. Again, doing basic data analysis using DuckDB. You submit, you can run everything locally and test, and then you submit to Gradescope, and your output has to match whatever the expected output is on Gradescope. Okay? Should you use an LLM? Yes. Try it. See how far you can get. But you need to understand what the thing's actually spitting out, because there might be an exam, might ask you some basic SQL questions. Okay? All right, so again, next class, I won't be here. We'll be in London. So there's no, Monday's a holiday, so there's no class for anybody. And then Wednesday we'll post on YouTube. Okay, so new classroom. So this is Drew. He's at DBT, and as I said before, this is arguably one of the most important applications in the data space right now. It's widely used everywhere, and it's super important. All right, so Drew, sorry for being late. Sorry for the technical mess up. The floor is yours. Go for it.
Great, Andy. Thanks for having me on. I appreciate the kind words. My name's Drew Bannon. I'm one of the co-founders of DBT Labs. We do make a product called DBT. DBT is definitely not a database, definitely not a data warehouse, but we help companies use their data warehouses and make sense of the data, in the database. I think I've got about 10 minutes with you today, so this is a sort of modified version of an onboarding session that I do for new employees, just talking about what DBT is and why it matters and how it fits into a broader ecosystem. So I got an apple pencil, let's sketch it out. So this is the setup that you'll see in a lot of modern data-oriented companies. They've got data coming from data sources. These are transactional databases like Postgres, MySQL. They've got advertising data and payments data, finance, telemetry, sales, customer support, you name it. What they want to do is extract and load all this data into a centralized place, data warehouse or data lake. And so practically what happens is they've got these extract and load processes that are creating, hundreds or thousands of tables loaded by different teams and different departments, sometimes duplicated, sometimes stale, but you just get a bunch of tables in a data warehouse. On the other side of the data warehouse, we have the consumers. So there's BI and data science dashboards, or notebooks or scripts that are querying these tables. You've got your ML and AI use cases pulling from maybe the raw data directly. And they've got operational stuff, like wanting to send emails to people who left, items in the shopping cart on an e-commerce website. So that's querying some more tables too. And so the net result is that there's a giant mess here. There's no semblance of data lineage, meaning that you can't actually see where the data is coming from that's powering this BI report, right? You just have to trust that it works, and usually it's wrong in some way. There's no documentation. So it's hard to find things like data assets that already exist. It's hard to reuse someone else's work. You frequently have to rebuild things from scratch. There's no semblance of a deployment process here. You just edit stuff in prod. You edit the dashboard in prod, you change the tables in prod, and hope you don't break anything for anyone. There's no sense of QA, which means things are broken all the time, quality assurance. And fundamentally, you get duplicated business logic for each of your different use cases or dashboards. And so here, we're kind of, imagine recalculating what it means to be a customer 100 times over. That leads to inconsistencies and broken. So the alternative approach here is the one that we take with DBT. And the big idea is, as before, we want to extract and load data into a data warehouse. But this time, we'll draw this imaginary line down the middle of the database. We'll say the left-hand side is for raw data, and that's where we extract and load, our raw tables loaded from our data sources. And then we have these blue pipelines here that I drew. So this is actually what DBT does. It takes your raw data sets and helps you create derived data sets that are, enriched or apply your business logic to the raw data. The net result is that you get these higher levels of abstraction and these tables that you can query. And basically, the data set that you expose to the business represents sort of the terminology that folks in the business use and not the raw data coming out of Salesforce or coming out of Postgres. So it's a sort of translation or transformation layer. The benefit of doing it with DBT is that you can source control your business logic as SQL code. You can visualize your data lineage, so you can see how data flows from raw tables through data models into dashboards. You can use an actual CI process, so you can develop code in dev and not in prod. And you can find out that your data is broken before the CEO hears about it, which is always the better time to find out that your data is broken. And finally, you can reuse assets. We've built this transform table. Other colleagues across the business can build on top of it. We can amplify each other's impact. So I want to show you what this looks like a little bit in DBT. The big idea here is that we're looking at a DBT model called Stage GitHub Stars. In this case, GitHub. We version controlled it in GitHub. And so Stage GitHub Stars is the name of our table. Here, STG, it's like a staging model. This is like going from your raw data to kind of one layer of preparation. You rename some columns for clarity, filter out invalid or deleted records and stuff like that, soft deleted records. And then fundamentally, our model code is just SQL. So it's select star from some source, and then we've got a little window function action here to deduplicate records by the first start update. The only difference between this and pure SQL is that DBT has a built-in templating language called Jinja, and this allows us to do pretty cool things. And specifically, it allows us to represent edges between different nodes in a dependency graph. So here we're saying stage GitHub stars. Stage GitHub stars depends on the raw source GitHub star users, in our case loaded by Fivetran. So that's fun. We can also do things like write for loops and iterate over tables and union a bunch of tables together with divergent schemas. There's really a lot you can do with this template language, but fundamentally what we're doing here is defining our business logic in SQL that gets version control. The net of it is that you get a sort of dependency graph that looks like this in DBT. So here's just a sample of an overall much bigger DBT dependency graph. And every single one of these nodes is either a data source, in this case these are sources, or it's a sort of intermediate transformation like we see here. So this is us breaking up a lot of business logic into smaller pieces, kind of like you would with functions, in another programming language. But each of these nodes in the graph is itself a table. And so there's some really cool stuff you can do with DBT, like casting your data sets or documenting your data sets. So we can create assertions that say, the invoice ID in this table should always be unique and not null, or something like that. And now we can find out if our assumptions about the data set don't hold, again, before the CEO does. Finally, we output a sort of dimensional model here. This is dim stripe customers. And that's what we want to actually expose to the BI tools or data analysts in the company who are querying these data sets and trying to answer questions about business. And I can guarantee you it is a much nicer experience for that person to query this table that has all the information that they need blended from 40 different source tables than it would be to go query those source tables directly. Because we did all this hard work kind of along the way to translate from the raw data sets into sort of the language of business. That was the 6 or 7 minute answer to what exactly is DBT. If you take anything away, it's transform data into data warehouse and do it like a software engineer would write code.
Okay, awesome. Any questions for Drew? Yes.
Yeah, so you mentioned that you write your data pipelines in SQL. Do you have an efficient execution engine that can run this efficiently over big amounts of data?
The question is, Drew, you mentioned that people define these DAGs through SQL. Do you guys have an execution engine that can efficiently execute these?
It's a great question. We do, and it's called Snowflake or Databricks or BigQuery or Redshift or so on and so on. So DBT, again, is not a data warehouse itself. What we do is we run queries on the customer's data warehouse, which for us, I think the biggest four are Snowflake, Redshift, BigQuery, Databricks. And so our customers really like that because they did all this work to get their data into their data warehouse. It's in their single source of truth. They want the data to stay there. So they like that DBT will connect to their Snowflake account or their BigQuery project and run the queries on the data, in C2 where it lives.
A large percentage of all queries that run on Snowflake, BigQuery, and so comes from DBT. It's massive.
This is lineage marketplace.
David, it's like a data lineage marketplace tool. Drew, you want?
Oh, interesting. Well, what I would say is, so we do two things, and maybe this diagram is confusing, but actually DBT's job is to create these tables. Think of each of these nodes as a table, or a view, could be a view. So DBT actually creates these based on the version control definition in your DBT project. But we also visualize it for you so that you can trace, where does the data come from that ultimately lands in the dim strike customers table. Well, you can trace it all the way back to these data sources and some other stuff over here that's not shown. But DBT's primary job is to actually build those data sets in dependency order. We just so happen to also visualize it for you as like debugging or data catalog tool.
All right, awesome. Let's thank Drew. No. Go for it.
If you were to look at a typical DBT model, basically, I should have said this part earlier. What we'll do is wrap your select statement in, create table as blah blah blah. And so this is how we push down the execution to the logic. The user's job is to define the business logic in a SQL select statement. DBT's job is to materialize that logic as tables or views or incrementally update tables, things like that. So that's how this all fits together.
All right, so you may not all realize the significance of what DBT is because you don't have any data, right? At some point in your life, you're gonna have a bunch of Python scripts try to mash this right? And then you realize this is terrible. How are you ever gonna maintain this? This is the problem that DBT solves, right? That's why I keep saying it's a big deal. It's widely used because it is a way to declare, here's my pipeline for my data projects. Whereas before it was just like a bunch of random stuff people would have in GitHub. Okay? All right, let's thank Drew. All right, thanks, man. Appreciate it. All right, again, Monday's a holiday, no classes, and then Wednesday I'm in London. That'll be on YouTube. And then please get started on Project Zero and the homework. Okay? Thank you. Hit it.
Cash money, flick flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain.